when you have compressed data, if it is to be read by multiple mappers in the MapReduce paradigm to parallelize it, it is essential that the mappers be able to start decompressing from a certain point within that stream. So each mapper gets a chunk of compressed data and needs to start decompressing. As a rule, most compression formats don't allow you to do that. The one difference is gzip 2, where it is easy to, on account of it being block-oriented, to be able to start in the middle of the stream and start decompressing. This way, mappers can operate in parallel, starting with compressed data within the stream. The other way to achieve splittability, since most of these formats don't give it to you out of the box, is to use the sequence file format, in which case the data is already divided, cut up into pieces, and then compressed. One point to be aware of is SEO, which used to be part of the Hadoop distribution, but is not any longer on account of licensing issues. However, it's still available for download and can be obtained and installed separately. And it works well with Hadoop. It's good to know all these compression formats, but all the heavy lifting is actually done in native code behind the scenes. So you can see over here that all the compression formats have a native option. So the second part of that last column tells you about Java native. Now, as a matter of fact, gzip 2 did not have a native option before, but part of the work that we did over here added that in, so that is why it is a y/y. In addition, the first three do have a Java option as well, which they can use under certain cases. When we talk about the trade-off, as I said, it's a tale of trade-offs in the beginning. And we looked at the trade-off that we made when we use compression. But the different compression formats that we have also engage their own trade-off. And this chart gives you some idea about that. On the y-axis over here is the time taken for compression, the CPU time, and this is the addition of both compression and decompression. And on the x-axis is the extent of compression that we can do. An ideal codec would probably be on the bottom right corner of the screen, where it would operate in almost instantaneous time and give us excellent compression. So we can see over here that zlib and gzip 2 emphasize compression ratio. They try to focus on reducing the size of the compressed data as much as possible at a cost to in CPU time. Whereas if you look at the other three, Snappy, SD4, and SDO, they operate really fast, but don't do as good a job at compressing. For all of these numbers, we used about 250 megabyte corpus from Wikipedia to get this data. And here's a quick overview of how to use data compression in Hadoop. In the case of the map job, as we said before, the file extension is used to detect the kind of compression, and the appropriate codec is used. The intermediate data that is generated by the map and that is going to be read by the reducers is controlled by the options in the second category over here: MapReduce, map output compress, and MapReduce map output compress codec. Similarly, the final output that is generated by the MapReduce job is controlled by the options under section 3 here. And in addition to using these properties, you can also indicate the type of compression to use if you are using sequence files, where you can say you want to compress one record at a time or a block at a time, or not at all. So how do you go ahead and choose which of these codecs to use? For the input data to the mapper, typically you might not have so much control. I mean, the data is already there. It will either be compressed or not compressed. If you do have a choice, you probably would want to compress it if it is large in size. And if you do compress it, in that case, ideally you're using something that is splittable, a format that is splittable like gzip. Or if the format does not have that option, you would use the sequence files. With regard to the intermediate output from the mappers that gets fed to the reducers, you would almost always turn compression on. I mean, this is transient data that doesn't last a long time, it's just there for the duration of the job. And if the data that is being generated is large, you would always want to use compression, especially if you've got spills being generated and there are network bottlenecks. Codecs like Z4 or Snappy would be ideal in this particular case. With regard to the output from the reducer, you would want to compress if you want to ship the data off grid. In that case, you would use a standard format like gzip or gzip. To improve your write speeds is another reason to use compression over there. And sometimes what happens is you are running multiple jobs. The output from one job gets fed to another job. In that case, you might want to use a fast compression algorithm like NZO or NZO. Compression is pretty integral in the Hadoop stack. Most components like pig, hive, and HBase have support for compression that's built on top of what MapReduce and Hadoop provide. So these are just generally compression options that you can use to control the way compression is used by these systems. If you don't specify anything, the fallback is to use the Hadoop options. So this chart just gives you a quick overview of that. With regard to pig, there is a 10-point compression because when you run a big job, it breaks down into multiple MapReduce jobs, and those options are used in that particular regard. For hive, there are several options where you talk about intermediate compression and the output compression. And for HBase, you can compress per column family, and there are many different compression formats that you can use. LZO, gzip, Snappy, and LZ4. You can either specify compression for HBase when the table is being created, or you could disable the table and alter it later on to specify compression. So here are some numbers that we obtained from our production clusters to give you an idea how compression is being used at Yahoo. So the purple part of these bars shows you compressed data, and you can see that for map tasks, most of the data that's coming into these jobs is compressed by zlib, 73%, and the other ones are much less. So almost 98% of the data that's coming into the map tasks is compressed on our clusters. With regard to intermediate output, it's even higher. We had a concerted push to try and encourage intermediate data to be compressed. So it's almost 99%, almost 100%. And almost all of it is LZO, as you can see. With regard to the final reduce output, part of it is compressed. There's quite a significant amount that is shipped off grid for data analytics. It might be uncompressed over there, but the compressed portion is used, gzip is used for the compressed portion. LZO is the biggest one, but that really reflects the prevalence of big jobs on our clusters. So that's about 55%. So we'll quickly move on to the second portion of the talk, where we're talking about the issues that we face with compression. As you know, we process a large amount of data at Yahoo, and a year ago we noticed that we were running out of storage storage space in some of our clusters. So to alleviate that, we try to use RC files instead of sequence files for the format. RC file is a slightly different format where data is stored in column media fashion. And by doing that, compression formats have a better chance of achieving higher compression. By doing that, we got about a 25% improvement in storage efficiency. The other option we looked at was to try and use gzip2. Now, gzip2 has achieves a better compression ratio than most of the other formats, but the cost is higher CPU load. And we thought of eliminating that CPU load by using a faster implementation of gzip2. In particular, this is the IPP library, which I'll cover in the next slide. The issue with doing that was that, as I said earlier, the gzip2 codec was one codec that didn't have a native code implementation, so it was not easy to substitute another library to do so. So we had to rewrite the library, and that was done in conjunction with JSON. This is available as GR8462, and was checked in. It's available in newer versions of Hadoop 0.2, 3.7 and above. Once that was done, we were able to replace the native code library with the IPP library. Now, what does IPP stand for? This is integrated performance primitives, a library supplied by Intel. This is a set of high performance modules that are available in a variety of domains, including compression, cryptography, string processing, image processing, and so on. The way this library achieves its speed up is through improvements in the algorithms. The algorithms are rewritten, plus they also use architectural improvements. Since modern processors have a lot of new instructions that are available now, compilers find it rather hard to generate code that will use those instructions. So Intel supplies libraries that uses the features in their newest processors. And these improvements are available by loading the appropriate primitives at runtime for the specific processor that is being used. In the case of compression, there is support for localized runtime encoding, borrow zero transform, SEO, and so on. And typically what you would use is a drop-in replacement for a high-level format, such as CLI, gzip2, or SEO. By doing that, you can get significant speed up. So what is the extent of the speed up? We use standard programs to measure the performance over here for gzip and gzip2. And for the other formats, we have specific libraries that we use. And they all run in 32-bit mode because the clusters run in 32-bit mode. The compression depends quite significantly on the kind of data that's being processed. And in this case, we use a variety of data over here. So this chart shows you compression ratio. On the y-axis, we have the file size in megabytes, and you can see the extent of compression that you can achieve. As you can see, ZLab and gzip2 do well in compression ratio, whereas the other three don't do as well. But moving on to the next page, we can see the other side of the coin. So this chart shows CPU time on the y-axis, and it gives you an idea about the improvement that the IPP library gives you. So you can see that IPP does better than standard open source CLI. The yellow chart bar here gives you the performance of the Wikipedia corpus. On the right side of the chart, you can see the similar improvement that's even better actually, almost 40% or more with IPP gzip2 over gzip2. Actually, we can also see that the Java version of the codec that was there earlier doesn't do as well as the other two. Now this chart shows you the fast algorithms, and they are all pretty similar. They're not very much different, although SE4 does seem to do better than both SEO and Snappy. The analogous chart for decompression performance. Now decompression is much faster than compression in all these cases, and although the trends are similar, the overall time for decompression is much smaller. Again, with decompression for the fast algorithms, we see LZ4 consistently seems to do better than LZO and Snappy for all the different corpuses we use. Now coming to compression, not standalone but within Hadoop, we used Gridmix to measure the performance with the internal performance framework with the standard mix of jobs. Our cluster was about 35 nodes, dual quad-core Xeon machines. Now this chart shows you how map performance pans out with the different gzip2 codecs. So we can see that the Java gzip2, regular gzip2, IPP gzip2 all do somewhat similarly, not very much different. The zlib is there just for comparison. We can see zlib does much better, but it doesn't compress as well. Going on to reduce, here we see a significant difference. By the way, the y-axis over here is in minutes as opposed to seconds in the previous chart. Reduce takes a much longer time. And here you can see that open source gzip2, the 28, is better than the Java gzip2. It's not as significant as the standalone performance, and that's because of the overhead of the JNI interface that is present. But we do see that IPP gzip2 does significantly better than open source gzip2 and Java gzip2. And the final chart over here shows you the wall drop time, the end-to-end job time, and the numbers over here are very similar to the reduce. You can see that IPP gzip2 does very well, almost coming to the zlib numbers. So there's quite a bit of future work that you could do. The native code gzip2 does quite well, but it's not splittable at the moment. It's not a major issue in the sense that it falls back to the Java implementation as splittability is requested. Pig does not use the codec yet, that work needs to be done. There are several other aspects that we worked on. They are all listed over here, I won't go into that. So finally, how do we select our compression? We talked about that a bit before, but here are a few of the points that you can use. The first is the kind of data that you're using. In our case, using the kind of experiments we ran, getting numbers and evaluating how the different compression formats operate on your data, will give you some guidance as to the kind of compression to use both for the intermediate and for the final output. If you are changing jobs, one job feeding to another, you might want to use a quick format like LZ4 or LZO. Data storage efficiency requirements like in our case, where you're running out of space in your clusters, might dictate that you should be using something like gzip2, a strong compression format that gives you a much better compression ratio. Sometimes your hands are tied and you are required to generate a standard format output, like gzip or gzip2. In that case, you can choose one of those formats. For splittability, you might have to use sequence-wise or perhaps gzip2. Finally, you may want to give some thought to using libraries like IPP, which have the potential to give you very significant performance benefits. And with that, I think I will open it up to questions. So,
a couple of related questions. LZO. I thought there was a splittable version of LZO. Somebody at Twitter or somebody implemented. Are you?
Yes. Yes. I didn't cover that because of shortage of time here. But LZO does allow for splittability, but it is not inherent in the format. With gzip2, the format allows you to divide the compressed data into chunks. With LZO, you need to have a separate phase where you take the compressed data and generate an index file. This index file will tell you where the boundaries are in the compressed data. And that index file has to be shipped across the Hadoop job, perhaps with distributed cache or so on. So it is not a standard, straightforward way to achieve splittability, although it can be done.
The other question is, I think you mentioned LZO can be used as like the intermediate stage for big jobs, right?
Yes.
So if it is not splittable between MapReduce jobs, how are you using it?
Sorry?
Between two different MapReduce jobs, how can you use LCO format?
You could generate the data in chunks as well and divide it up into pieces. And you know what the sizes are. So when the data is generated, it can be divided into pieces and fed into these other jobs that are there.
If you're just running a regular MapReduce job, like pig, you are not doing anything specific, right? So it's automatically writes to HDFS. So then it has to be splittable.
Yes, you could generate the data in pieces, and the next other job, the other mappers that come after the big job, can take those splits and operate on the splits. Yeah, we can cover that.
Which version of the Xeon supports the IPP or any other process that was the AMD or something?
Which version of the processor that we use?
Yeah, the Xeon, which version of the Xeon supports the IPP?
I think it is a 5620 or something of that sort. It was one of the newer versions. I don't know the exact number, exact model here, but I can do that to you.
Do you need to install anything or correct the processor, or it's by default available to you?
Are you talking about the library, the IPP library? Yes, the IPP library will work on any Intel processor. So it's not specific just to Xeons. What it does is it actually uses the features of the processor that are available, going all the way back to the earliest processors. So those don't have those instructions, so it won't use them. For the newer processors, whatever instructions are available, it will use those specific features.
More questions? Okay, thank you very much, Rohan. And see you at September 18th.